That's a super cool intro. So, welcome to this talk. My name is Ricardo. I work at CERN as a computing engineer. I also have a couple of roles in the CNCF, in the Technical Oversight Committee, and related to end users and the research user group. Today, I'll be talking about some challenges we have at CERN with scaling big deployments, and give you some feedback about how we try to scale those out, and also focus a bit on software distribution. I like to do live demos. There's always something wrong with live demos, so I'll immediately apologize for it in case it breaks. But this time, I decided to play safe and use production services. But guess what? If you look at the interventions happening today at CERN, there's an intervention where the registry will be down for 7 minutes between 10 and 11, and this talk starts at 10:45. So this is how lucky I get. So there's a 7-minute downtime chance in the next few minutes that this breaks miserably, but let's see. All right, so the reason we have big workloads is because at CERN we also have big machines. So it's we try to see the very small matter, very small particles, try to find the infinitely small, but actually we use very, very large machines. So you probably all know about the Large Hadron Collider. It's our most recent particle accelerator, 27 kilometers in perimeter, 100 meters underground. You have the Geneva airport here for the scale. We have these big experiments where we collide protons, and then they look like this. This is actually a picture of the Atlas one in a cavern 100 meters underground. You can see the person there for scale. This is a long time ago when it was being built. These days it looks more like this. Again, you have some people there working for the scale. It's a 40 meters high cavern, completely full with this detector. So this is just to try to understand why we have these needs. In reality, we make billions of collisions every second, and we do something like 40 million pictures in these detectors per second, and then we have to store all this data. So this poses a challenge in terms of computing, data storage, data distribution, a bunch of stuff. So we end up with pretty large applications. And today I'll start by focusing on what we just saw. So this detector here is Atlas. There's two parts of the picture. One is where we try to scale the data collection at the detector level. We call this online computing. And then we have the offline reconstruction of the events and analysis. So I'll focus on that by taking one example from one of the experiments called Atlas. So Atlas is this experiment. We saw the picture. You have a model of the detector there on the top. We have all these collisions, and then we use rather large farm that is inside the detector cavern underground, where we try to do this online filtering of the data. The goal is to go from something like 1 petabyte a second of data that we generate inside the detector to something like on the order of tens of gigabytes a second that we can store and later analyze. So I have a video here that I hope it plays nicely. It does. Awesome. So let me try to. So here is a picture of what happens. So we have the protons going in two directions in the accelerator, and then at some points where we install these experiments, we make them collide, and we have the events coming, and then we try to record them. So we see here the events will start happening. We try to record them. The result of this is obviously just data. This data then has to be filtered immediately because it's too much, and we use different levels of filters. So the first level is this trigger level 1, which is basically based on hardware, and we are mostly dumping most of the data, as you can see. And then we have this second level filtering, where we use what is already a computing farm to do some additional filtering, a bit more careful. And then after this, then we bring the data up, and we store it in our data center at CERN as well. So this is just to give you a picture of why we have these needs. So this farm has some challenges, because when we have Beam, and this lasts a couple of hours, we want to run the Beam applications. But when we don't, when we are, for example, trying to inject a new beam because the old one didn't have quality anymore. We want to make best use of these resources for simulation. So this poses a challenge because if we look at it, wait, that's not what I want. Sorry. All right. Nope. Let's do it like this. So what we want is to basically run these filters on this farm. I mentioned the numbers. The farm has around 3,000 nodes these days. The challenge is that we have to run 30,000 applications in parallel. So we saw the talk from Thomas this morning where someone asked what's the scale that Cilium can work on. And he mentioned that the challenge is not the number of nodes, is the number of workloads and how often they come and go. So this is exactly the problem we have here. We have to launch 30,000 applications in less than 90 seconds when the beam is announced. And then we have to put them down and run simulation workloads when the beam is down. So we have this challenge of doing it fast enough. So in 2017, we did a study to see, can we replace the existing infrastructure for this farm with a large Kubernetes cluster? And this was Kubernetes 1.5, and we found quite a lot of challenges here. So when you try to do this kind of scaling up really quickly, we saw that the scheduler and the components in Kubernetes were not up to the task at the time. So we were getting something like 12 containers a second starting, which is very far from achieving in 90 seconds 30,000 applications starting. So we started understanding with what the issues were, things like the number of queries per second that different components can do to the API server. We interacted a lot with Kubernetes 6 scalability, and we reached something like 57 containers per second, which was much better. And gave us some hope to continue. So last year, we actually did another round of this study with Kubernetes 1.21, and we started trying with a much larger cluster with 2,500 nodes, which is closer to what we need in production for this use case. And we can see that with some set of configuration of number of pods per node, and with 2,500 nodes, we can actually start the applications we need in around 70 seconds, which is within the line. And if we extrapolate this to the prediction of a 5,000 node cluster, we're actually under the target. So this means that for the next run, which will start in a couple of years, this infrastructure will be running purely on Kubernetes. So this is a really nice transition from where we started, which was running services and simple workloads, to where we are now, where the core business starts also depending on these technologies. So we talked about online, where I mentioned 30,000 applications. These are pretty standard applications in the sense that you start them, they stay there for hours, maybe a couple of days. We have other sorts of workloads and challenges which are more in the offline computing. So when the data comes, it's what we call raw data, and then we have to reconstruct the events. And basically what we're doing is generating even more data, which is always a good challenge to have. But to do that, we need a lot of computing, but this is purely batch-like computing. And what we want is basically to go from the raw data to generate something that we call event summary data, and then finally analysis objects, which are the ones the physicists are actually looking at. So this is like just jargon. But basically what we need is a lot more resources for that. So in the last 20 years, we set up a distributed computing infrastructure that we call the grid, has around 200 sites around the world connected with dedicated links. And roughly the physicists see this as a gigantic supercomputing computer, but in reality, there's a lot of complexity in the infrastructure. So the dream here is to see these sites as Kubernetes endpoints and see the whole thing as a Kubernetes endpoint for a sort of distributed batch system. Now, the challenge, if you look up there, is that at any moment in time, we have around 250,000 jobs running. So this poses a pretty big challenge. When we start talking about single cluster, this is basically very hard to manage. So things like multi-cluster and what we heard also today, cluster mesh are things that we really want to focus on. But first, we need to sort out the missing bits for the scheduling itself. So When we talk about Kubernetes, we talk about pods. Individual pods are not really the unit we're interested in. We're interested in workloads. A workload can actually generate multiple pods. If you have some sort of like MPI job, you will actually break the workload into multiple pods. If you have things like Spark or Hadoop jobs, it will do the same. You'll give it a data set, and the actual workload will decide how many units it should have for processing. And then we need queues. So these workloads are submitted to queues, where it's an extra level of scheduling, where things are waiting for some space to come in, but also gives the scheduler the opportunity to scale resources or to instruct the controller managers to scale resources as required. So the second thing we need is these queues and priorities. It's you have a large cluster that is multi-tenant. You have all these teams and in our case, experiments submitting workloads. You need a way to somehow distribute the quota and the resources from them. Not only that, we also have heterogeneous clusters. We are talking about CPUs, GPUs, maybe even in CPUs, multiple architectures. So it's always a problem. So you need to have this kind of intermediate matching between the queues and the flavors that they support. And then the second bit that I put there is fair share. So this is something that is not common in more traditional IT services as a requirement, but it's critical for batch, which is we have a large data center with, I don't know, 100,000, 200,000, 500,000 cores. When someone doesn't use the total quota, we don't want to waste those resources. So we want to do some sort of sharing of them so that others can scale up and fill in. But at the same time, we want to be fair. So this should be compensated if you look a bit further in time. And this is where this concept of fair share comes in. And in this specific implementation, it's a tool called Queue that is being developed in the SIG scheduling in Kubernetes. This is called a cohort, which is to join multiple queues so that things can move between. It's very, very much what we need, and we're following this very closely and trying it out. And then finally, we need concepts like gang scheduling or array jobs, which is to tell the scheduler that different instances or different jobs are actually related to each other and should be started at the same time. Otherwise, they will just be consuming resources for no reason. So a lot of development has happened in the last year or so. If you're interested in this, I put some links. There will be a dedicated day in KubeCon in Chicago. We are actually merging the HPC and Batch Day with the machine learning and AI because there's so much overlap. And I put here the links of groups that could be interesting. And next, I'll talk about software. So we talked about applications. We talked about workloads. One thing that is really a challenge for us is scaling software distribution. So if we look, I found this diagram while preparing this talk. If we look at lines of code, the Linux kernel has something like 29 million lines of code. I actually don't know when this was generated. It might be much more now. But if you look at what CERN is doing, like Atlas is the experiment we saw just before. Athena is the software that backs up a lot of the computing in Atlas. And if you add this to the trigger and data acquisition software that we talked about as well, we're actually in the order of 6.5 million lines of code. So it's significantly large. If we compare this to an old experiment at CERN, like Aleph from like 20 years ago, it's significantly larger. So scaling this is a challenge. Not only that, but I found some slides from presentations at CERN back in 2003. There were two challenges. Why do we have so much code? It's actually because this software was written so long ago that even common libraries for messaging, for persistency had to be developed, and a lot of them just stayed, and it's very hard to transition to new libraries. This happens slowly. Not only that, they have a pretty aggressive release cycle where this massive software is released something like every 3 weeks, which poses a huge challenge when you're talking about the distributed computing infrastructure all around the world. You have to push this software somehow everywhere. These containers really helped with this, with packaging everything and giving people a unit that they can manage and install. It was pretty chaotic to do it before. But it also poses a challenge because containers were actually not designed for this kind of amount of data. So I gave a talk a few months ago where I mentioned the challenges about container images. And starting with the very well-behaved images, we have Alpine with 3 megabytes compressed, 6 uncompressed. So this is basically the disk space you need, and that's what you need to transfer. And then you need to look to Ubuntu. It's a bit larger, but like who has to manage images that are larger than this? I guess everyone. Yeah, so let's say you have your admin utils image that has, okay, close to 1 gigabyte, maybe 1 gigabyte something disk usage. So who has to manage images that are larger than 1 gigabyte? Still quite a lot. But then we get to the serious business, which is we have to handle this software where a single image is 19 gigabytes, and when you extract it on the nodes, it's 60 gigabytes. That's for one, and we are releasing every 3 weeks. So this is pretty chaotic. If we have to push this to thousands of nodes constantly, just the traffic and to make this scale is huge. So we kind of started a ranking internally, which was a really bad idea because people get challenged. But when I did this presentation, I actually started getting messages of people that find funny images around. So this is the one that I got last week, which is in Colab. The runtime image for Colab, the one that everyone is using, is 24 gigabytes. And I got a message saying, why do they need this? And look, take it for your list. So we started realizing this is actually not us. There's a lot of people doing similar things just because there is a need for it. And it's very hard to structure it otherwise. Now, we still have the winner, as long as I understand. I don't mention what this is, but it's 76 gigabytes, a single image, 125 gigabytes uncompressed on the disk. Now, the funny thing here is that this is a perfectly reasonable use case. This is an engineering application which traditionally is this big. And we started not only running microservices in Kubernetes, we started running like end-user applications because they need GPUs, and we can move these workloads to a central pool of GPUs instead of paying for everyone to have a desktop with a GPU on their desk. This means that the application has to run on this containerized environment, which means these things exist. So it poses a challenge. So we knew this challenge existed, and back in 2019, we organized a workshop back at CERN where we brought a bunch of people from the community, and we explained our needs. And we actually knew or had a good idea of how to solve this, because when we had to handle this software distribution back in the days, we developed a read-only file system that we called CERN VMFS, which is basically a hierarchical set of squid caches where we have the main center at CERN, and then we start scaling to distribute this as squid caches in the different sites. So this concept was already quite familiar to us. There was something being worked on that was called the Containerd remote snapshot, and I'll briefly mention what this means. So the idea is that instead of pre-pulling the image before you start your workload, you're actually mounting a remote file system that is in your registry that is backed by the HTTP calls that we do to the registries. But basically, you start immediately container with this remote file system as your rootfs for the container. And then you explore a really nice idea, which is or OCI images are tarballs internally. If you have a normal tarball, there's no way you can find anything inside. And you have to go through the whole thing. But actually, a tarball of tarballs is still a tarball. So you can then have a seekable tarball, where you can then basically wrap every single file in its own gzip, put it all in a tarball, and then you can do HTTP range requests to request individual files. So this allows us to basically remotely mount and only download the files that the workload actually needs, even if the image is 18 gigabytes. We actually did some tests, and we realized that around 6% of these images are used by our jobs. So we are actually distributing and using the network for no reason. And this also builds up nicely with the previous talk about environmental sustainability. So there was another optimization, which was one problem is that if you start a container like this, you actually lose a bit of time at the start. The application should be running, but actually it's downloading the files it needs, so there's a sort of weird time at the beginning. So there's this enhanced strgz that basically builds on the definition of what's in the entry point of the image to set prioritized files that should be immediately downloaded. And there's even a way to start a container while you build it, run the entry point application, identify the files, and then build them in this prioritized list. So this is a very nice idea. This is how it looks. As I mentioned, you have the registry, and then you're doing HTTP range requests. And then on the node, you have containerd doing this remote mount for your rootfs. And this works beautifully, and we actually use it already quite a lot. This actually went beyond our community. So if you're using GCP and GKE, they announced something in 2021 called image streaming that is a very similar concept, and it's available. And the use cases they are targeting is things like faster autoscaling, fast port startup. It's very keen to like functions and sort of serverless workloads. And then they also say something like, I highlighted it here, it says to have benefits of image streaming during the first pull of an eligible image. So they're actually mixing the concepts we also had. They have a local cache in the region, and then every cluster is actually pulling from that local cache. So it's very similar to what we are trying to do. So I'll try this quick demo that might break miserably. So what I'll try to do is deploy two workloads. One is using standard images, and the other one is using strgz. And we'll see how it goes. So I'll start by just doing this, and you will see that the workloads should start very quickly because the images are already there. So this is kind of cheating. But I want to show you that the first set of nodes are using a standard image, is this std, and the second set of nodes will use this strgz images. So what I will do is I will delete this, and I will be very aggressive about cleaning the nodes from the images they have. And I will just show you here, this is basically the monitoring of the traffic in two of the nodes. This one is using the standard image. This one is using the strgz. So when I will deploy, we'll see how long these workloads take to start, but you will also see the amount of network traffic that is going. So this is a bit aggressive. I'm going to the node and making sure that the image is definitely not there. And I will also run a quick check so that I can prove that. All right, so now it's just checking that there's no, I called it KCD image, so the image looks like this. Should have it here. So this is it. So there's this KCD image, and it has a STD tag and strgz tag, and this is what we are looking at. So I'll deploy this again. And if it all works, the five ones below, they basically started in 5 seconds. This image is 6 gigabytes, 6.4 gigabytes. And it would pre-pull it, take quite a long time, like the other one is doing. It will take a few seconds. While in the bottom, we just started immediately. And it's basically only fetching the files as the workload will need them. What we see also is that the strgz node is using very little of the network. It actually started without using any. But then if we look at the standard node, it's using something like 400 megabytes a second, or millibytes, while it's pulling the image. Now it's done. Now it's extracting the image. This also takes quite a long time. So in the end, it took something like 50 seconds for the first ones to start. And we have the other ones took like 4 or 5 seconds. So it's a huge gain. And we're talking about 6.5 gigabytes. And if we check the, so I just wanted to show you here. So this is the images now that are pulled. You can see that there's a slight difference between the standard and the strgz of like 0.01 gigabytes. This is because of the overhead of the extra tarball metadata. So it's a very small price to pay in the size of the image. So this kind of worked. I wanted to show one more, which is this one, which we should be able to see if this is working, because I'm tunneling. Let's start again the tunnel. There we go. And we should see these bumps. OK, I did a test run just before. You can also see, like, Prometheus is not querying the data very often, but you can see the first set of nodes on the top are the standard ones having a higher transfer rate than the lower ones. And if we look at the disk utilization, we would see something similar. So there's a slightly higher utilization on the nodes that are using the standard image because they extracted the image locally. All right, so this kind of worked as well. So I'll finalize and then take a couple of questions. The only thing I would like to conclude with is that this won't stop. We know this. We keep having not big applications, big workloads. We also have constantly big needs for more things. So what we would like is this idea of a centralized cluster where we can run all our workloads for all sorts of things with on-premises CPUs and GPUs, and then scale out to whatever else we need, like TPUs, GPUs, IPUs, FPGAs. And we would do this using the public cloud. This has huge challenges, like we heard today. There are multiple ways of doing it. We've been trying them all. So we started in 2017 with Federation V1. This was very easy to use, but it had a lot of limitations. So we came up with Federation V2, which had much less limitations, but was definitely not easy to use. So that didn't work very well either. Then we tried this idea of virtual kubelet, where we have a node that is in the cluster, but it's actually a virtual node that is backed by the Kubernetes API itself. So we could integrate a remote cluster in a public cloud into our cluster by seeing it as a node. That also has a few limitations. Now, the one we are looking now in 2023 is this idea of this cluster mesh and also this larger mesh across administrative boundaries with this idea of transit gateway. This is really promising. It's something we'll be working on testing in the next couple of months. Now, the other challenge we have is that we have a very big, large hardware collider. But actually, we have a proposal for a much larger one, which the proposal is just starting. This will take a long time, but the idea is this 100-kilometer-long accelerator that goes through Lake Geneva. So that's the city of Geneva. The airport suddenly looks much smaller. So yeah, we don't know what's coming, but something big will definitely come after. So thank you very much, and I'm happy to answer any questions. One up there.
What happens to the application if it tries to access a file that is not downloaded yet? Will it be just a long I/O, or?
Yep. Yeah, that's what it's doing. It feels like a long I/O. Yeah. So some applications might be a bit sensitive to that. That's where this idea of the enhanced SRGZ becomes quite important, because if you run the workload and you download these files, you kind of mitigate a lot of that problem. But then it really depends on how fast the registry the connection to the registry is and low latency you have. Like if it's a remote registry in some other location, it won't work very well. But if it's a local cache in the data center, it's quite performant.
Thanks.
One related issue is when it breaks, when the file is no longer available. So this is the corner case where things break very aggressively. Yeah.
Other questions? We still have time for one more. Down here.
Yeah, so I think about the StarGZ files. How do you calculate, what things you want to pre-cache locally? Is that something you can provide hints for, or?
You mean which are the priorities files?
Yeah. So yeah. You want prefetching.
So this is done at build time. You need to put this knowledge inside the image itself.
Right, so you provide hints, yeah.
Yes, and the way this is done, you can do it really dummy just by putting it, whatever is mentioned on the entry point in the Docker file or whatever artifact you're using. Or you can do a more fancy one, which is to actually launch a test workload. Which is usually described in the entry point. And during the build, we'll actually launch the container, let it run for a few seconds or maybe a minute, identify all the files that are being touched, and we pre-cache all this.
Yeah. Great. Yeah, that would be.
Yep.
Thank you very much. There is sadly no time for other questions.
Thank you.